If a function z equals f of xy has a maximum or minimum at a certain point, a, b, then the first order partial derivative with respect to x at that point is 0, and it is also 0 with respect to y at that point. So you can see that these tangent lines have a slope of 0 at that high point, and the same thing would be true at this low point. And so here's what we have to do in order to find out whether a certain point is a maximum or a minimum. So we take the first order partial derivatives, the first time with respect to x and the second time with respect to y. We define d, which is called the discriminant, by this. It's the second order derivative, first time with respect to x, second time with respect to x, times the second order derivative with respect to y both times, and subtract from that the second order where you take it with respect to x the first time and y the second time squared. Now, you'll remember, I hope, from previous sections that if you take the second derivative first with x and then with regard to y, or with respect to y then with respect to x, it doesn't matter. Okay, that's why it can be f of xy here, or it can be f of yx, because those come out to be the same. Now, here's the test. Find d by multiplying those second order derivatives, okay, at the point that you find when you find the first order derivatives and set them equal to 0. Okay, if this calculation comes out to be positive, but f of xx comes out to be negative, then you have a maximum. Okay, so that's the discriminant is greater than 0 and f sub xx is less than 0, it's a maximum. But if the discriminant is greater than 0 and that f sub xx, that's the derivative with respect to x, and the second derivative with respect to x again is positive, then you have a minimum. So if they're opposites, you have a maximum. If the discriminant is greater than 0 and f sub xx is less than 0, opposites, then you have a maximum. But if the discriminant is greater than 0 and the f sub xx is greater than 0, you have a minimum. And if the discriminant comes out to be negative, then you have a saddle point. And if you get the discriminant equal to 0, this test doesn't work for the particular function you're working with. So let's look at an example of one of these. Find all local maximum, local minima, and saddle points of the given function. F of xy equals 2x squared plus 3xy plus 4y squared plus 7x plus 11y. So the first thing we have to do is find the first order partial derivative with respect to x. That means we treat x like a variable and y like a constant. So 2x squared would be 4x for the derivative. 3xy would be 3y. If x is a variable, 3 and y would be the coefficient there. 4y squared, there's no variable, so that's a 0. Plus 7x would be plus 7. And then plus 11y is also a constant if x is your variable. So that is our first order derivative with respect to x. Now let's find it with respect to y. With respect to y, this first term, no y's in there, that's a constant, so it's 0. With respect to y, the coefficient would be 3x. The 4y squared would be 8y. The 7x would be 0, and then plus 11. So these are our first order partial derivatives with respect to x and with respect to y. So we set each one of these equal to 0. And this is a system of equations. and we've got to solve these simultaneously. So I'm going to just go ahead and move my 7 over by subtracting it, and move my 11 over by subtracting it, although it's fine to leave it, leave those on this side. I just prefer to get my constants on the other side. Now I have to do something to these equations to eliminate either the x's or the y's. So I'm looking at these first two, and I know that they have 12 in common. So if I multiply the first one by 3 and the bottom one by -4, I can get a 12 here and a -12 here, so that when I add the equations, I get a 0. So that's a 12x plus 9y equals -21, and a -12x minus 32y is +44. So make sure you multiply all the way through, including over here to this constant on the other side. That's a common mistake. When I add these together, 9 minus 32, that's going to be -23y equals 23. I divide by -23, so y equals -1. Okay, now that's only y. I've got to find x. So I have both of these equations that have x and y, and I can use either one. I'll just go, and you can do either of these or either of these. But I'm going to go back up here to the original, and I'm going to say 4x plus 3 times -1 equals -7. Remember, that's equal to -7 when we move that 7 over. That's 4x minus 3 is -7. Add 3. 4x is -4. And x is -1. Now this is called our critical value, or our critical point. So we don't know if this point is a maximum for this function, a minimum for this function, a saddle point for this function, or none of the above. So what we're going to do is we're going to apply our test. Okay, do you remember what the test was? You have to take the second order partial derivatives. So I have to find f(x(x), f(y(y), and f(xy), or f(y(x). Those come out to be the same, so it doesn't matter. All right, so we go back to our f sub x, 4x plus 3y plus 7, and notice that for that, the derivative with respect to x is 4. We go back to our first order partial derivative with respect to y, and we see if we take the derivative of that again with respect to y, we get 8. And then if we go back to the first order partial derivative with respect to x and take it with respect to y, we get 3, right? Because that says we've taken it once, and now we're going to take it again with respect to y. So we look at the y, and its derivative is 3. So remember, the formula is f(x(x) times f(y(y), xy. That's this ordered pair. And of course, we don't have to substitute the ordered pair because these are constants here. They don't always come out like that. If they do, you have to put that point in. f(y(y) of xy minus f(xy) of xy. So we get 4 times 8 minus 3 squared, that's going to be 9, and then that's 32 minus 9, which is 23. Now that's D. D is greater than 0. Okay. Now we have to compare this to f(x(x). Okay, so D is greater than 0 and f sub xx is greater than 0. That means you have a minimum at the point -1, -1. So since this is a minimum, we say that there's no local maximum, but we have a minimum located at -1, comma, -1. And there are no saddle points.